program. I would like to take you on a brief tour and show you some of these activities. We have been actively involved in the shuttle program for several years. We build the orbiter mid-fuselage at Air Force Plant 19 in San Diego. We have delivered the first article on time and within budget. We will start producing the second article, which is the structural test vehicle, in July of this year. I believe our intimate knowledge of the mid-fuselage has and will continue to be of significant help to our work on the I.U.S. We recently completed our contract with the Navy on the validation phase of the cruise missile program. This is a design-to-cost program, and the program manager did utilize our Convair integrated management system, which has tri-service validation. We won that program. I intend to use the knowledge and the experience that we gained on your I.U.S. program.
Our full-scale, earlier in the presentation, our I.U.S. system is comprised of two main airborne elements: the I.U.S. vehicle itself and the ASE cradle structure and ASE avionics. Our full-scale mock-up incorporates these two segments in a simulated shuttle cargo bay. What I'd like to do now is to review some of the basic elements of the system and demonstrate the rollout sequence. At the initiation of deployment, an electromechanical actuator rotates the upper portion of the cradle in the I.U.S. vehicle outward approximately 74 degrees. You can see that the I.U.S. and spacecraft are firmly guided out of the cargo bay. The geometry of motion is controlled so that no fore and aft or lateral spacecraft clearance is lost. All the I.U.S. vehicle equipment packages are located in the four control module bays at the forward end of the vehicle. Even with the vehicle enclosed in the ASE structure, these packages are directly accessible. The second phase of deployment. Spacecraft have reached the full rollout position. Vehicle and spacecraft checks may be accomplished either through a hardwire link through the probe or by RF link with the ground. When the payload is ready for physical separation from the orbiter, the deployment probe extends about 8 inches, disconnecting the umbilicals. A second actuator retracts the probe pawls, freeing the I.U.S. One of the significant benefits of our cradle vehicle system is the fact that loads are transferred in a uniform manner between the ASE structure and the vehicle, thereby allowing lower vehicle structural weight. This is accomplished by our circumferential joint design. To verify the clamping concept, this functional scale model of the forward axial load interface ring was manufactured and tested. The model verified opening and closing force requirements, clearance and relief geometry considerations, and axial force reaction capability. The model was tested with normal and simulated crash loads. Tests were successful, and the data indicated lower deflections and stresses than predicted. Thus, as you can see, deployment of the I.U.S. flight vehicle and its valuable payload is simple and straightforward. It is independent of the orbiter-supplied deployment mechanisms, which can then serve to provide another means of redundancy. Our full-scale, dimensionally correct engineering mock-up is and will continue to be a means of verification of design concept, resulting in a fully integrated I.U.S. system.
I would like you to see our avionics redundancy lab. Dave, would you explain what we're doing here?
Thanks, Ken. The objective of our redundancy laboratory is to have a mechanism where we can reduce to practice designs, ideas, and techniques that looked promising for the I.U.S. program. By reducing designs to practice, we can eliminate subtleties that may have been inherent in a particular design approach. During the past year, our laboratory has been configured both in a triplex and a dual string configuration. The 3 computers you see here are 32,000-word 16-bit machines, the same size as our baseline computers. During the course of our laboratory efforts, we have fabricated and tested 3 channel selectors, a hard switchover dual channel unit, a central value selector for use with a triplex system, and the unit you see here, which is our dynamic dual channel selector. Data from our redundancy laboratory was used to support our soft failure trade study. These precision strap-down instruments were used to support our analysis of power spectral density of gyro drift. This data was necessary to be able to correctly calculate gyro failure thresholds. This carousel gyro was evaluated during the month of April. Data from a circus gyro will be evaluated in the next few months. An accelerometer dodecahedron was built last year. Data from this instrument cluster was invaluable in helping us develop our redundancy management software. Our avionics system is driven by a separate ground computer simulating the LPS components. Our LPS simulator has a 3-color graphics console where we can display both operator messages and system data. The work in our laboratory over the past year has been invaluable in assuring that the system and components we propose to use on the I.U.S. program will fulfill their intended missions, and to ensure we technically lead our potential avionics subcontractors. During the validation phase of the I.U.S. program, our laboratory will continue to be expanded with additional software and hardware until the system evolves into an operating I.U.S. breadboard in 1977.
The compatibility of our baseline configuration with expendable launch vehicles gives the Air Force the programmatic option described in our alternate proposal. Davy Jones will demonstrate. Davy?
Thank you, Ken. Our I.U.S. configuration will place 5,400 pounds to geosynchronous orbit in the shuttle. By removing the I.U.S. configuration from the cradle and applying some simple kit modifications, the configuration is compatible with the Titan and will place 3,680 pounds to geosynchronous orbit in this configuration. We retain the existing Titan interfaces. In order to minimize programmatic risk, we have initiated activity in development of the propulsion system utilizing the same approach we used in avionics. That is, proof of concept by hardware demonstration. We have completed 300-gallon scale-up and initial characterization of our 88%, 18% aluminum HTPB propellants, including burn rate demonstration, mechanical and bond strength tests, accelerated aging, and space storability testing. Kevlar filament wound case technology being developed for the Air Force Aerojet MX program is directly applicable to our I.U.S. Full-scale burst testing and motor firings are scheduled for later this year. Test results will be directly applicable to our I.U.S. propulsion system. Our reaction control system subcontractor, Rocket Research Corporation, has already completed vibration, life, and minimum impulse testing on our I.U.S. hydrazine reaction control system. Thus, we are progressively reducing the programmatic risk by logical sequencing of hardware demonstrations.
Convair's I.U. He was the test conductor on the first Mercury launch. He's activated 5 launch complexes. His latest assignment has been as base manager of Convair's operation at Vandenberg Air Force Base. Tom Phillips, System Effectiveness. was Assistant Site Manager for Launch Operations, Inspection Supervisor, Chief of Quality Engineering, and recently directed planning at Convair for the Nuclear Quality Program certification. Russ Babcock, Manager of Material, has been responsible for all major subcontract activity at Convair for the past 10 years. Seymour Zinkoff was a project engineer on the initial Centaur development program, Manager of Manufacturing Development, Operations Manager of the Kearney Mesa plant during the development of the improved Centaur. Dave Geyer, Manager of Avionics. He comes with proven credentials. He recently completed the development of the improved Centaur avionics system, wherein reliability and cost were of paramount importance. My other team members have similar experience. They've worked together and compiled an outstanding record of achievements.